Have you ever been just incredibly frustrated when an AI agent completely forgets what you told it literally 10 minutes ago? You're having this great productive interaction, and then suddenly, poof. It's like you're starting entirely from scratch. It is a massive roadblock in AI development right now. Well, welcome to today's Explainer, where we are unpacking a really fascinating solution to this exact problem. Elastic recently open-sourced a brand new agent memory system called Atlas. And what makes Atlas so special isn't just the code itself. It's that it actually borrows fundamental principles from human cognitive science to create a true scalable memory for AI. Let's get right into it. Here's our roadmap for today's Explainer. We're going to start with the context window trap, explore the human brain solution, break down the 3 types of memory, walk through the memory consolidation process, and finally, dive into the database debate. All right, Section 1, the context window trap. Why more tokens simply isn't the answer. So the core issue we are dealing with today is the challenge of scaling agent memory. Right now, when developers deal with users who have a really long history of interacting with an AI, they just hit a wall. The standard kind of easy workaround in the industry right now is to just take all of that prior interaction history and stuff it right into the AI's context window. Basically, you're just feeding the AI an incredibly long transcript of everything that has ever been said every single time you prompt it. But as you'll see, simply having a massive 1 million token context window is absolutely not the same thing as having a true, persistent memory system. In fact, Elastic is incredibly blunt about this flawed approach in their documentation. They state point blank, a 1M token context window is a Scratchpad. It is not a memory system. If you're just dumping raw text into a massive prompt window, you are essentially just giving the AI a giant, temporary piece of scrap paper that just gets thrown away. And why exactly does this Scratchpad approach fall apart in a real production environment? Well, first off, it completely breaks down on cost. Processing 1 million tokens for every single user interaction is unbelievably expensive. Second, you run into unacceptable latency. I mean, users don't want to wait 30 seconds for a reply while the model reads a literal novel's worth of text. Third, there's this well-documented phenomenon called the lost in the middle effect. This is where AI models simply ignore or forget facts that are placed far away from the edges of the prompt. If your most important information is buried right in the middle of a massive context dump, the AI routinely just misses it entirely. Simply put, stuffing the context window is not a scalable long-term solution. Which brings us to Section 2, the human brain solution. Cognitive science meets AI. This is exactly where Atlas comes in. Elastic identified what's totally missing in AI right now, and that's long-term memory. Atlas is designed as a persistent store. That means it actually survives when you close the session, and it's built to scale up to years of interaction. Instead of dumping everything into a Scratchpad, Atlas lets an AI retrieve specific facts by content, by time, and by user. It functions so much more like your own long-term memory, pulling up only the highly relevant information right when it's actually needed. So how does it do that? Section 3, 3 types of memory, how Atlas categorizes data. First up is episodic memory. Think of this as the raw, totally unedited timeline of your life. In Atlas, episodic memory captures what happened. Every single user input is stored as a distinct, individual event. It's basically the raw log of the conversation. But as humans, we don't remember every single word of every conversation we've ever had, right? We abstract facts from those events over time. And that brings us to our second category, semantic memory. This captures what's true. The system actually analyzes those raw episodic events to identify durable, superseding facts. It separates the important long-term truths from just the everyday noise of the raw chat log. Finally, we have the third category, procedural memory. This captures what works. Over time, the AI learns how to act and how to actually solve problems. Atlas stores these as playbooks, which are essentially series of steps designed to solve a specific problem. It's exactly the difference between knowing a random fact and knowing how to ride a bike or execute a complex task. Now, taking that biological theory and turning it into hard technology takes some real engineering. Because episodic, semantic, and procedural memories function so fundamentally differently, Atlas creates a totally separate Elasticsearch index for each distinct type. Why? Because each type of memory requires its own specific rules and life cycles. To make the whole shebang work seamlessly with your agents, Atlas integrates via the Model Context Protocol, or MCP, and critically, they ensure strict per-user isolation. By using document-level security, or DLS, Atlas guarantees that a query only ever searches the memory documents belonging to that specific user. So your AI won't accidentally cross-contaminate one user's long-term memory with another person's. Moving right along to Section 4, the memory consolidation process, turning events into facts. Here is how an AI memory actually lives and breathes. Step 1, the user inputs data, and it's stored as an episodic event. But here's the really clever part. Most of these raw episodic memories are allowed to just naturally decay and fade out of memory, exactly like our daily conversations do. However, in Step 2, an LLM is asked to actively consolidate them. The LLM reviews the events, identifies the new durable facts, and stores each one as a short semantic sentence. It even keeps the supporting episodic memories attached as evidence and tracks if this new fact supersedes an older one. Finally, in Step 4, it uses these consolidated facts to create or update those procedural playbooks we talked about. And speaking of updating those playbooks, there is a brilliant mechanic built into that consolidation process. Atlas maintains success counters and failure counters for its procedural playbooks. So when a playbook successfully resolves a user's issue, the success counter ticks up. By actively updating these counters based on real-world outcomes, Atlas intentionally biases the retrieval results. The system naturally boosts the procedural playbooks that are actually successful in practice, which makes the AI way more competent over time. Now, to actually pull the right memory at the exact right time, agents access Atlas via a heavy-duty query engine. When an agent needs context, it fires a single hybrid query that searches across all 3 memory indices simultaneously. It uses reciprocal rank fusion over both a BM25 lexical search, so your standard keyword matching, plus a GINA v5 semantic search to truly understand the actual meaning of the query. Finally, it takes all those merged results and re-ranks them using a cross-encoder just to ensure the absolute most hyper-relevant memories are passed to the AI prompt. And the result of all that heavy lifting? An incredibly impressive 0.89. That is the Recall at 10 score Atlas achieved when it was rigorously evaluated on its question-answering capabilities. To put that into perspective, it means that 89% of the time, the absolute correct piece of context was found in the top 10 results returned by the memory system. That is highly, highly effective context retrieval. Which leads us to our final section, Section 5. The database debate. Is Elasticsearch overkill? So over on Hacker News, this really interesting debate popped up. One user asked a totally fair question, seeing as Atlas is built on top of Elasticsearch. They asked, is using Elasticsearch as the storage overkill? What about other vector-capable databases like SQLite? It's a very natural question, right? Developers almost always want the lightest possible tool for the job. So why bring in a heavyweight infrastructure if a lightweight database can handle vectors? Well, another developer jumped in with a reality check, breaking down exactly why simpler databases fall apart at scale for a system exactly like this. First, Atlas requires complex operations like scripted scoring to weigh those success and failure counters we just looked at. Second, for performance, you absolutely need approximate nearest neighbor, or ANN, search capabilities. The defender pointed out that while simpler brute force vector searches are surprisingly performant early on, they hit a hard latency wall well below 1 million vectors if you expect fast web page type response times. Yes, maintaining Elasticsearch isn't free, but picking an underpowered database for an AI memory system, hitting a wall, and then having to completely port the system later is a massive time-consuming headache. Robust infrastructure is completely validated here because true memory scales incredibly rapidly. And that brings us to our final thought for today's explainer. As we finally move away from the era of simply stuffing context windows, you really have to ask yourself when looking at your own systems, is your AI just using a Scratchpad, or is it actually building a memory? By leveraging the cognitive science principles of episodic, semantic, and procedural data, Elastic's Atlas provides a fascinating blueprint for what scalable, truly intelligent agent memory looks like moving forward. Thank you so much for joining me, and I'll see you on the next explainer.